Hello, this will be a video that will walk you through the data analysis for Aspirin Part 3, spectrophotometric analysis. Again, that's part of our Chemistry 2 sequence at York College of Pennsylvania. And after we've completed the data analysis, I'll spend a couple of minutes discussing the overall report that you'll write for the aspirin experiment. Given that it's such a large report covering 3 weeks of experimental work, I want to make sure you're well prepared to do the best possible job on that. This report is also worth 25 points in the laboratory grade. Okay. But let's begin first with our data analysis. You don't necessarily have to use a spreadsheet, but as I considered the work that you'll do, I think a spreadsheet's a quick, easy way to set up the calculations because there is going to be some repetition in the work that you do. So I've generated a quick spreadsheet thinking about the data that you collected today. You made 5 standards with salicylic acid, so we're going to need to determine the concentrations of those, and we'll be making a graph from that data, so I'm prepared to do that. And then for your unknowns, which would be your raw aspirin from your experiment, your recrystallized aspirin, and then the samples of commercial store-bought new and old aspirin. Those will be our 4 unknowns that you'll have absorbance values for, and we're going to try to determine purities of all of those. So I've laid out, and this follows the analysis sequence in your laboratory manual, but I think this will be a very quick and efficient way to conduct your, your calculations. So the first thing we need in order to determine all of the concentrations of our standards is the mass of salicylic acid that we used in our first 100 milliliter sample. So I've got a group of students who's going to share their data with me. How many grams did you use?
0.183.
0.183 grams of our salicylic acid. This needs to be converted to moles. So 1 mole of salicylic acid is 138.12 grams. So that means we have 0.00131 moles of salicylic acid. Now this was dissolved into, if you recall, a 100 milliliter volumetric flask. So the concentration of our salicylic acid standard would be 0.00131 moles divided by our 0.1 liters, or 0.0131 molar. We then took 1, 2, 3, 4, and 5 milliliter samples, respectively, out of this stock solution, as we often call it, the stock supply, and repeatedly dissolved or diluted each of those into a new 50 milliliter container. So that is the dilution rule. M1V1 equals M2V2. And what we'd like to know for each of those new solutions is what is its concentration. So M2 is going to be M1V1 divided by V2, where our V1s are our 1 through 5 milliliters, and our V2 was always 50 milliliters. It's this type of repetitive calculation, or a pattern, and M1, by the way, is the number that we just found, that's perfect for this portion of a spreadsheet. So in this cell in the spreadsheet where we want to find the molarity of our standard, we can simply build this formula. It would be equals the molarity that we have, 0.00131, times the initial volume, so that's going to be A3 in this case, divided by 50, the total volume. Okay? And that will calculate the formula. Okay, again, so that was our concentration times our volume, A3, divided by our total volume. And then Amanda grabbed again the bottom corner and filled that down. I've also added 0 as one of our data points, which you're instructed to do in your lab, because this is a realistic point. When there should be no concentration of salicylic acid, the absorbance should be 0 as well. So now we can fill in our absorbance values. Can you guys call out your absorbance values for starting with the 1 milliliter standard?
0.411.
0.411.
0.845.
0.845.
1.27.
1.27.
1.692.
1.692.
2.080.
2.8.
And
2.80.
2.080.
Sorry, 080. And then a 0 for that. Okay? All right. Now we want to make our Beer's Law graph. As we discussed in the pre-lab, a graph of absorbance of these solutions versus concentration should be linear. And because I've entered in my molarity into the first column, absorbance into the second, I should just be able to highlight these cells, beginning with the molarity and dragging down, and then go to my insert scatter graph. There we go. And we should have, yep, just checking the numbers, we have our absorbance values on the y-axis and our concentrations on the x-axis. All right. What we need is the equation of this trend line. So we right-click on one of the data points and choose to add the trend line. Now we want to make sure that we have the right type. Linear is the usual option that's available. That's correct. Okay. We want to have the equation and the r squared value. If we really wanted to, we could force our line through the 0, 0 point, since this is a practical point, but we won't bother with that for this part of the analysis. So now we've got our equation. And this equation, if you could drag it out here to the clear space, this equation is going to be very important, because our equation, while it's written in y equals mx form, y is really our absorbance. It's telling us the absorbance of any solution containing salicylic acid will be equal to 15,996 times the concentration of that solution plus 0.002. So we now have 4 unknown solutions, unknown in their concentration of salicylic acid. We can use this equation to work backwards to find that concentration. Okay? So let me first rearrange here. That would be absorbance minus 0.002, and then divided by the 15,996. That will give us the concentration of salicylic acid in any solution, prepared in the exact same way that these standards were. So we can drop this graph down out of the way now. And then what we need are the absorbances of some of our unknowns. Okay? So how about the raw? I'm going to list them out. Raw, what was the absorbance of our raw solution?
1.816.
1.816. Of the recrystallized?
2.82.
2.82. How about the new commercial?
0.144.
0.144. And the old commercial?
0.293.
0.293. Okay. So now, there's a typo in my concentration. Now I need to, in the concentration column, I'm going to calculate these concentrations using this formula that I just described. So we need to type in this formula. That would be, begin with an equals sign. We would open a parentheses. We would reference our absorbance, so that's E3, minus the 0.002 value, and then close the parentheses and divide by the 15,996. And again, we can fill those down. So not only have we done it for one, but now we've done it for all 4 of our solutions. We've got the concentration of salicylic acid in each of those. The next step in the analysis calls for us to convert our concentrations to moles. Each of these solutions was in 50 milliliters. Okay? So the moles in any solution are always equal to the molarity times the volume. We just found the molarities, and this is the volume. So each of these would be equal to the respective molarity value. That's F3 times 0.050, because 50 milliliters needs to be converted to liters. It's going to be a pretty tiny amount. We were working with very small quantities. Okay. So this tells me how many moles of salicylic acid were still in my raw sample of aspirin that we generated. To get the mass then, well, we're just doing stoichiometry. Mass is always moles times the molar mass. So our moles are now in column G, so G3, times the 138.12. So this is really taking, X moles times 138.12 grams per mole. Just like we began our initial calculation for getting our stock solution. Okay? So we've typed in equals our mole quantity in G3 times the molar mass, and we've filled that down. Okay. So now we know how many grams of salicylic acid were in each of our samples that we prepared. Now each of those samples had a unique mass. You were given a certain amount to try to fill that out. So now we need to actually provide those masses in here. So guys, what were our sample masses for our raw sample that you weighed today?
0.173.
0.173. Recrystallize?
0.167.
167.
0.163.
163.
0.157.
0.157. Okay. Now, this sample was a mixture of salicylic acid and acetylsalicylic acid, or aspirin. And what we've done to this point is figure out how many grams of salicylic acid are in each of those samples. So the rest, or the difference, would simply be the mass of aspirin. So the aspirin mass is simply going to be equal to the sample mass, I3, minus the salicylic acid mass, H3. Okay, so this is sample minus salicylic acid. Okay. Hopefully you won't get any negative numbers. If you get a negative number, which I have seen occasionally, it is most likely because you've had some error up to this point giving you an improbable salicylic acid mass greater than your sample mass. And it really should not be possible. You'd have to check for a decimal point error perhaps, maybe you're off in your dilution or something like that. Okay? Now we can express these masses of aspirin in terms of the purity, percentage purity. And so purity is always going to be the mass of the aspirin divided by the sample mass times by 100, so that it's on a purity scale. So we have these numbers in different columns. So this would be our aspirin is in J3 divided by our sample mass, which was in I3, and then we multiply by 100. And fill those down. All right. Now, so we can look at our values here, and actually, so I'm seeing a little bit of a complicated story when I look at these numbers. They don't tell us exactly what we would have hoped to have found. Here it would look like our recrystallization did not improve the purity of our sample of aspirin. Okay? And it would also look like our old aspirin is more pure than our new aspirin in this case. Neither of which makes a lot of sense, actually. Ideally, what we would see is that the recrystallized purity is greater. Hopefully that agrees with your qualitative test that you completed in week 2, and that the new has a greater purity than the old. It's a little counterintuitive, especially the new and old, thinking here because of the higher absorbance that would mean more salicylic acid being present, but a smaller sample mass, I guess, is what led to that difference right there. Okay, we did do the division correctly, right? Equals J divided by I. Yep, that looks like it should be correct. Okay. At any rate, we've walked through all of the calculations now, and so we're done with all of the data. Now, the data template for this part of the experiment doesn't necessarily match this, but it would be totally fine if you went ahead and did this type of analysis and then cut and paste this from Excel into your final report. Keep in mind, you will need to show examples of these calculations and formulas in your lab report, even if you do that. And that's what the template usually has, is the spaces for you to put that in. If you choose to cut all that template out and put this great looking table in there, which, you know, if I was grading it, would love to see, just please be sure to show the examples and the formulas that you use. And you can do that separately. They don't all have to be merged into the template that we do. That's a perfectly good option if you'd like to do that. Okay. All right, let's go ahead and talk a little bit about the overall lab report that you have. I can have the projector turned off at this point. Thank you. All right. So your overall lab report is going to be quite extensive. And I want to make sure that you understand all of the things that you should be including in it so that you don't give away points by accident. All right. So we'd like these reports to begin with an introduction. Of course, you're going to need a title, you're going to need your name, your partner's name, date, all that good stuff, okay? But you need a nice introduction for this experiment. 3 weeks worth of work, certainly worth spending a few minutes time setting the stage, okay, for why this was important work and what we did. Aspirin is one of the most commonly used medicines in the world. So let's get a little background information on it. It is not hard to go out and find some easy information on aspirin. And it's quite interesting as well to learn a little bit about the history of aspirin. There's connection to willow trees, I think you'll find, and just some other neat important marks along the road to bring it to being aspirin. Okay? So find a little bit on the background of aspirin if you could. Right? Now, anything you get, be sure to reference. I know that in your writing classes at the college, you've been taught the proper techniques for referencing and citing information that you have taken from another source. And I do not for any second believe that any one of you is the person who generated this information about aspirin that you're sharing in your report, at least on the history of aspirin. So don't forget to reference it. There will be an automatic deduction if you fail to include the reference citation and if you fail to actually use the proper in-text citation, even either a footnote or in-text parenthetical reference, both being very, very important. Okay? So after you've done your introduction, you're going to want to have a procedure section. Now we did 3 weeks worth of work, so be sure to include all 3 weeks. Be brief. You need to highlight what you did in each week. Week 1 was the synthesis. Be sure for week 1 to include the reaction. you should be able to generate the reaction with, the Chem Draw feature that we have available on all of the computers here. Maybe Amanda can bring up Chem Draw, and I'll briefly show you how to do that in a couple of minutes. All right. So this would be an important thing. You're showing someone, here's the reaction that we did in week 1. All right. Then you're going to want to describe what were the qualitative tests that we did in week 2. What was the quantitative test that we did in week 3? So a brief overview of the procedures that you did in each week of the experiment. Okay? All right. Then you're going to want a data summary. Okay? There isn't much data from week 1, although you do have the mass of salicylic acid that you used. Okay? And then from week 2, you should have the mass of aspirin that you recovered. From week 2, you've got qualitative data. In past years, I've seen students organize this nicely into a table where they say what the test was and what the result of the test was. Okay? Melting point, they give the melting point range. Iron 3 chloride, they give the iron 3 chloride color. All right? So there are ways that you can take qualitative information and put it into a nice summarizing table that makes it quick and easy to see and read. You could also give bullet points perhaps for each of the qualitative tests as the results. Okay? Or sorry, as the data at this point. Okay? And then in week 3, obviously your data would be the mass of salicylic acid for the stock solution, and then the mass of the samples, and then the absorbances. This is the actual data. Again, not the results yet that we just went through and got in the data analysis. We want the presentation of the data first. All right. After the data section, you need a calculation section. Percent yield would be a calculation that you'd want to show from week 1, spanning into week 2 when you collected the mass of your aspirin. There are no calculations that were done in week 2, the qualitative tests, and then the week 3 calculations that we just talked about. Either show them in the data template, or again, if you're going to use the Excel table that we just generated, you can show separate formulas, okay, and examples for any one of your trials. Please, you don't have to do it for all of the trials, but take for example, the raw, take that all the way through from start to finish as an example, showing the reader how you did that. Okay, so you want to include the graph from week 3. Okay, that's part of your calculations that you made. All right, so save some room or cut and paste that in as well. Then you need your results. Again, your results summary, just like your data summary. So it should really parallel what you've done here for your data, but now you're not presenting the raw data values, you're presenting the calculated answers. Okay, so for week 1, that would simply be the percent yield. For week 2, you could take the qualitative tests and replace what the color was and imply what the meaning of that was, that it is pure or not pure. Okay, what the melting point range was, you could replace that with this means a pure, okay, or an impure sample, okay, as a way of modifying the data into the results. Okay, and then certainly you have lots of results from week 3 to include there. Okay. And then finally, we have our discussion section. And more so than any other experiment, you should have plenty to discuss with your aspirin. Okay? Again, the idea of the entire experiment was it a success? You began this experiment with salicylic acid. Did you end with salicylic acid, or did you end with aspirin? Do you believe, do you literally believe that what you have is now aspirin? Okay? Compare the purities. Did the recrystallization, did it benefit us? Did we get a more pure sample? You spent a fair amount of time on that recrystallization back in week 1. And the premise was that it was going to improve the sample of aspirin that you had. Comment on that now. Was it worth your time to do that? Did it benefit the experiment? Okay. Compare the new and the old aspirin. Does aspirin degrade quickly? Hopefully you kept track of how old your old aspirin sample was. If it's, more than a year or 2 old, now you might understand why when they sell aspirin, there's a best if used by date on it, because it is decomposing, turning back into salicylic acid in the bottle. Okay, just sitting there on your shelf. Okay, some other things for you to consider in your discussion. Do your qualitative and quantitative tests agree? Okay. Would it have been enough to simply do the qualitative test? Did they give us enough information about the purity of our aspirin samples? Okay? So these are all great considerations for us to have in our discussion section. You should definitely be able to fill out a good paragraph to 2 paragraphs on these topics. What was your yield like? Did you get a very horrible percent yield, okay, in this process, and why or why not? What went wrong with the recrystallization? Perhaps you lost a lot of your sample. Or if you think back to visually seeing stuff drawn down through the filter paper, I know I saw in the lab a lot of solid floating in the bottom of those filter flasks. Okay? And then at the end of your lab, you need to have your references. Any sources for where you've gathered information for your background. Okay? And so it'd be great to see 1 or 2 references down here in proper formatting. Okay? So all of that should take care of your report. It should give you a really nice report. The things that lead to automatic deductions that you really want to avoid are, first of all, you don't want to omit any one of these. Okay? Not even something simple like title page, or not a whole page, but the title information. Okay? Not having the reaction scheme is an automatic deduction. Not having those references is an automatic deduction. Not showing example calculations is an automatic deduction. Right? So otherwise, the rest of the report will be divided into these sections, and your instructors will be grading you on each of these sections. 4 points or so per section on average. Right? 4 or 5 points. Right? So that should help you generate a really nice report for this experiment. You only have just over about a week to generate these reports, which is not a lot of time. So I hope you'll get started, and that given this framework, you can take care of that report. All right, let's pull the projector back up and look at the ChemDraw program real briefly, which can help you write your reaction in. Okay? So we're using, again, it's ChemDraw, although the program on our lab computers is called BioChem 2012, I think, or BioChemDraw. Is that 2012? 2010. Okay? It's in the Chem Bio Office folder. Okay. When it opens, it brings up a template or a palette, like a drawing palette, for you to generate compounds and structures and reactions in. Okay? It actually has a very nice feature that will allow you to use. You can use under the structure menu, you can use the convert name to a structure, because you know the names of the compounds that you began with. So if you click on that, you can type in salicylic acid. And that's the salicylic acid structure. Okay? Now real quickly, actually bring the mouse over. The mouse does some different things. Notice it's a hand now, so it's going to grab. When she takes it off of the structure, it turns into a lasso. Bring it over here real quick. A lasso that you can click and drag around to highlight things. Okay? And then the other option is that when the box is available here, it should allow her to rotate the compound, although we don't want to do that in this case here. All right? Okay. So let's take our salicylic acid and bring it over to the, whoa. Oh, you didn't have, yeah, just undo, I say Z, or there we go. Actually, another way to draw the box is a different way to grab things, and then you get everything that way. There we go. Okay. Now we can use our structure, convert name to structure again. And the other ingredient or reactant was acetic anhydride. Okay. Now we need a plus sign. So we can use the letter, just like you would in inserting a text box in other Word or Office features. You click in text box so you can put a plus in. Okay. Now we need a reaction arrow. You can see on your data sort of template of tools here. This one clearly looks like it has arrows on it. You can take your choice. This is a forward arrow, forward reaction, so it's fine to use any one of the forward arrows. Okay. Now we're kind of running out of space, so maybe we should grab our box and highlight everything and again pull it over to the side a little bit more. Okay. Okay. And now we again want to insert our two products. Let's try aspirin. Let's see if it recognizes aspirin. It might not recognize the trade name, but it might. Some compounds have a trade name, aspirin being one of them. Its formal name is acetyl salicylic acid. You could type either one in. And then the other product is acetic acid, vinegar, right, is generated way back in our original reaction. Yeah, it's fine if we put it down there. You could resize and space things around. We probably need another plus sign in there. Now there's one other thing in this reaction. We added in strong acid, sulfuric acid. So we would generally, use a text box and type in H with a plus sign, and that represents acid. And then if we really want to be great, we would highlight the plus sign and then use our superscript tool. There we go. Okay? Now we can highlight this whole reaction, copy it, paste it into Word with the rest of your data, or the rest of your report, and it fits seamlessly in, just like a table or any figure that you would put into Microsoft Word. So look, that was like 2 minutes, 3 minutes, so it should be very easy for you to follow this and generate your aspirin reaction to include. All right? You'll definitely use this in the future in your chemistry courses that you take in the future, like organic chemistry, so it's great to learn a little bit about it now. This program is only available on our chemistry computers, so C217, the laboratory that you're used to being in, C209, the little conference room near the chemistry laboratory area, and then the organic chemistry laboratory. So if any one of those spaces was open, you could make use of that. I highly recommend spending a minute or two to generate the reaction while you're in the lab, and then copying and pasting it into a Word document, saving that Word document and emailing it to yourself or saving it on your H drive, so that you have it done and can put it into your paper at a moment's notice, and you don't have to be in the chemistry lab when you complete that part of the lab report. Okay, so work on that ahead of time, and then you'll have it saved for later use. All right. With that, I think we've covered everything, and you should be well placed to wrap up the aspirin report. I hope you have a great set of data that ties all together, and that you generate a really nice report.